Hello guys. So in this video we are going to see another scientific series problem which is delete and in BST, delete node in a BST. The problem is categorized as medium. Skin in the problem. Given a root node reference of a BST and a key, delete the node with the given key BST, return the root node reference or the updated of the BST. Okay, so our task is to we have given a BST tree. Inside the BST tree, a key is given. So we need to delete that and return the root node reference. So possibly updated one, which means after deletion we need to delink it with another elements below that. That's what mentioned here. And basically, the deletion can be divided into two stages. One is search for a node to remove. The node is found, delete the node. Okay, delete option will be into two stages. One is find the node and delete the node. That's it. So example is given here. 5, 3, 2, 4, 6, 7. Here we need to find 3. And after deleting 3, the 3 will look like this 5, 4, 2, 6, 7. Alright. So after that, the main thing about deleting in BSD is it needs to conserve its structure. So what I mean by structure is in BSD we have one thing. One is left subtree values should be less than root value and right subtree value should be greater than root value. Just remember this is very important to solve the show. Okay, so the output is here. And here they have given another output, which is also a correct answer 52467. So we'll stick with this. It's easier according to coding purpose. And example 2 is given. So 0, 3 does not contain a node with value 0. So if nothing is there, just return the root, nothing much. If root is null, key is 0, then return null. Alright, let's see the constraints. The number of nodes in tree is in the range 0 to 10,000. Sorry, 10 power of 4 or 10,000. Okay, 10 or 10,000. It's around 1 lakh. And node value is minus 10 power of 5 to 10 power of 5. Each node has a unique value. It is very important constraint because in BST it could also have duplicate. If it has duplicate, it makes our work even more complex. You need to delete all the duplicate values. So that's not the case here. All it has is unique value. And the root is a valid binary search tree. Okay, so if the root means valid binary search tree means it also follows binary tree, which is and root node should not have more than 2 children. Should be have maximum of 2 children or 1 children or 0. And the key is in the size of minus 10 power of 5 to 10 power of 5. So before getting into solve the problem, let's see how to solve this problem theoretically. Okay, so to delete a node from BST, I have given a sample tree and all the possible deletion process, not all the possible deletion process, all the possible cases that we could encounter. First, we have to delete a node with no children. Second, we have to delete a node with 1 children. And third, we have to delete node with 2 children. These two are fairly easy, but this one, we need to do something bit complex. Don't worry, I'll make it easy for you. Case 1, here we have the same tree. I have copy pasted it and we need to delete 1 from this tree. So first case is node with no children. So 1 has no children. We just have to derefer it from the tree and that's it. We are done with deletion. So case 2, delete the binary tree that has 1 children. So here 25, and if you see the original tree here, it has 23. Okay, so we need to delete 25 from this tree. For that, what we need to do is just refer this 23 to 25. That's it. If we refer this 23 to 30 and just dealing this 25, that's it. We are done with deletion. So 1 and 2 are fairly easy. Case 1 and 2 are fairly easy. And let's see the case 3. So in this case, what we have to do is we need to delete 30 from the tree. So 30 is here. What we have to do is we need to delete 30 and make the tree still follows the binary structure, binary search tree structure. So what we can do is we need to replace this 30 something uh, else to make this as binary tree. So what we can do is we need to find the minimum of right subtree, because the minimum of right subtree can be replaced in the root. Why I'm trying to say this, we can't place 23 here. If 23 is here, then 35 will come here, 33 will come here. So that's not the correct way to do that. What we have to do is we need to replace the minimum of right subtree, because the binary tree follows this structure: left subtree less than root and right subtree. If the root is deleted, minimum of right should be the next root, right? Minimum of right means minimum of here values in the left subtree. So minimum of right is left subtree, correct? So it is left of this 35, but 30's right is this subtree. So inside this subtree, we need to go to the last element, that is last node of the left. That could be the minimum. So if 33 is replaced here, the tree follows the binary tree structure: 33, 23, 35, 40. Alright. So this is how it goes. This is how we should handle the case. When we have to encounter deleting a node with two children, we need to find the node. First 30 is found. After that, we need to get into the right subtree of the 30. Inside that right subtree, we need to find the minimum value, which means the leftmost node value, because that put the only possible value which can replace in the place of 30, and still we follow the binary search tree structure. So I hope the cases understood, have understood it. And let's try to code these three cases in the problem. I'm trying to run that. And so let's try. Start. First, the base case: if root equal to null, return null. All right. So then we have to handle with case 1, case 0, and case 1. If root dot value, the value that we have right now, let's say we are in 5 and our value is 3. So if root dot value is less than key, so okay, here root dot, first we'll start with 5, that value is 5 and the key is 3. So now the root dot value is greater than key. In that case, what we need to do is root dot root dot left equal to delete mode of, we are traversing it again. So root dot left will be like delete node of root dot left. We need to pause the left because it's smaller. Else, if root dot val is less than key, in that case, root dot right equal to delete node of root dot right comma key. Just in case it's neither smaller nor bigger, in that case we need to handle what if root is found. If the root is found, we need to handle all the cases. So first we'll have 1 with no child and 2 with 1 child. So for this case, if root dot left equal to null, consider we are deleting 2. Okay, just for the question, deleting 2. In that case, if it has nothing, if and 2 has 1, say 2 has left subtree of 1, root dot left equal to null, return root dot right. So we are trying to delete, and 2 has 1 here. Let's say 2 has 1 here. Root dot right is null. In that case, 2 left right of 2 will be null. So we need to replace 2 with 1. And to refer this 2, we need to return what is here. So if root dot right is null, then let's say we have to return root dot left. So we need to return root dot left. All right. So these two cases handle. What if both these are not coming into picture? We need to delete true. Neither left is not null and right is not null. In that case, we need to find the first step. Replace key with minimum of case right subtree. So for to find that root dot value, we are replacing the key. So root dot value equal to find minimum. I'll define the function minimum and minimum. Minimum of value, we need to pause the root of right because we need to find it from the uh, right side of the subtree. Right side of the subtree, so we are pausing root dot right, and we need to find the minimum value in the root dot right. So for that, what we have to do is okay. So let's pause this root dot right. That's fine. That's enough. We will have root dot value. We'll just replace the root dot value. So after that, once the root dot value is found, we need to delete the node which is in the last. So if you are okay, let's go here. So if 30 is replaced with 33, we need to delete this 33, right? So to write that, root dot right equal to delete node root dot right. We are deleting the value which has repeated, which is root dot value. Okay. So let's define if it's done. Just return group. So if it's done, let's define this min value. We need to return the minimum value from the right side of the subtree. To do that, string out of float int min is equal to, let's consider node dot value. Okay, while no if node dot until we need to iterate it until the last of the leftmost node. So node dot left not equal to null, then min equal to node dot left dot val node equal to node dot left. We are going to another leftmost node. We are doing it until we encounter the last left node of the right subtree, then returning. Okay, my bad, sorry. Just a moment. Okay, just a moment, guys. I don't know why it is suddenly crashed. Okay. So, okay, we have got all the code here. So, return min. That's it. Let's try to run this code. Okay, it has accepted. The test case is accepted. Let's try to summon this. Okay, guys. So it has accepted and runs with 0ms. So the runtime 0ms. The code has O of n complexity because we are just iterating the tree only once. So for new problems, keep watching the videos and subscribe to. It will be helpful and we could get even more videos. Thank you, guys.